Good evening, and welcome back to Science to Sleep By. Tonight, we take on one of the most mysterious questions of existence, a question that humankind has whispered under the night sky for thousands of years. Does space end? As you settle into your bed, let your mind drift beyond the walls of your room, beyond the Earth itself, and into the vastness of the cosmos. Together, we'll explore what scientists know, what they imagine, and what may forever remain a mystery. This journey is not about racing to answers, but about gently unfolding the layers of wonder that surround us. So, close your eyes if you wish, let your breathing slow, and allow the story of the universe to carry you into rest. Since the earliest moments of human curiosity, one question has hung over our species like the stars themselves. Does space end? It is the kind of question that feels so simple when spoken aloud, but unravels into countless complexities as soon as we attempt to answer it. To imagine the end of space is to imagine a place where there is nothing more beyond. No stars, no galaxies, no further extension of distance, just an edge. Yet when we close our eyes and picture this, we cannot help but wonder, what lies beyond that edge? Is there a wall, a barrier, some sort of final boundary? Or is the very concept of end meaningless when applied to something as vast as the universe? The infinite question is not just scientific, it is deeply philosophical, pulling us into a confrontation with the limits of our imagination. The idea of infinity is notoriously difficult to grasp. Infinity is not simply a very large number. It is something without end, without limit, something that cannot be counted, measured, or fully comprehended. When we apply this to space, the difficulty becomes even greater. If the universe is infinite, then every direction you point, every step you imagine, every light year you travel, there will always be more beyond. If the universe is finite, however, then there must be a border, a place where space itself ceases to exist. But here lies the paradox. If we reach that edge, can we not ask what exists outside of it? The infinite question leaves us suspended between two impossibilities, a universe that goes on forever and a universe that has an end, but somehow is bordered by nothingness. Ancient thinkers often struggled with this same puzzle, even if they lacked the scientific framework we have today. For them, the night sky was both a map and a mystery, filled with lights that raised more questions than they answered. Some cultures believed the heavens were a dome stretched above the earth, a physical ceiling that curved overhead and held the stars like lamps. To them, space ended at the dome, and beyond it lay the divine, the unknown, or the unreachable. Other cultures imagined the universe as an infinite ocean or as an endless void into which the stars were scattered. Though these early attempts were born of imagination rather than science, they reveal the human need to confront the infinite question, to try and tame it with stories, metaphors, and symbols. The difficulty in considering whether space ends lies partly in the limits of human perception. Our senses evolved to navigate forests, rivers, and mountains, not to comprehend galaxies billions of light years away. We understand beginnings and endings in terms of books, lives, and journeys. But when we project that sense of beginning and ending onto the universe itself, we stumble into paradoxes. If space has no end, then it is something so vast it defies our evolutionary wiring. If space does end, then we are forced to imagine something outside of space, a concept that makes little sense to our minds. The infinite question lives in the gap between human intuition and cosmic reality. Modern science has given us new tools to explore this question, but it has not simplified it. In fact, the more we learn, the stranger the question becomes. Consider the concept of the observable universe. Light has a finite speed, and the universe has a finite age, so there is only so much we can see. The most distant galaxies visible to our telescopes are not a wall, not an end, but a horizon beyond which we cannot see, because light has not had enough time to reach us from farther distances. This observable horizon is like standing in the middle of a vast plain shrouded in fog. You can see to a certain distance in every direction, but whether there is more beyond the fog remains unknown. To many cosmologists, the universe does not end at that horizon. It continues, possibly infinitely. But because we cannot observe past it, the infinite question remains unanswered. One of the greatest complications of this question is the expansion of the universe. Since Edwin Hubble's discovery in the 1920s that galaxies are receding from one another, we have known that space itself is stretching. This expansion means that the farther away a galaxy is, the faster it moves away from us. At a certain distance, galaxies move away faster than light itself, making them forever unreachable, no matter how long we wait. To us, that looks like an edge of sorts, but it is not an edge in space, only a limit to what we can observe. The universe could continue far beyond that point, stretching endlessly, with galaxies we will never see or know. The infinite question grows sharper here, because even if the universe is infinite in size, our access to it is eternally limited. Philosophers and scientists alike have wrestled with the nature of infinity, not just in space, but in mathematics and logic. Some infinities are larger than others, as Georg Cantor showed when he described different sizes of infinite sets. This mathematical insight deepens the mystery of whether the universe is infinite. If it is, what kind of infinity is it? Is it an infinite grid of galaxies stretching forever, or something stranger, like a universe that loops back on itself, creating the illusion of infinity without ever truly being endless? These questions blur the line between science and philosophy, forcing us to expand not just our instruments, but our very way of thinking. For the ordinary person, lying in bed at night and gazing at the stars, the infinite question can be both terrifying and comforting. Terrifying, because infinity implies a scale so vast that our lives seem smaller than a speck of dust. Comforting, because infinity also suggests that existence itself is boundless, that there is no edge where everything simply stops. Some find peace in the idea that we are part of something infinite, while others feel dizzy, as if staring over a cliff with no bottom. The human heart responds to infinity with awe, and awe itself is a form of understanding. When we bring this question into a personal perspective, it becomes more than abstract. Does space end is also a question about our own search for boundaries, our desire to know what is out there, and to situate ourselves within it. Every time we ask the question, we are really asking about our place in the cosmos. Are we small beings, in a finite enclosure, or travelers adrift in an endless sea? The infinite question will never cease to fascinate, because it reflects not just the limits of the universe, but the limits of human thought. Even if one day science provides an answer, whether finite or infinite, the emotional power of the question will remain, echoing in the hearts of those who look up at the night sky and wonder what lies beyond what they can see. Long before telescopes, long before satellites, long before we had the ability to send instruments into orbit and measure the faint afterglow of the Big Bang, humanity's understanding of the universe came only from what could be seen with the naked eye. For most of human history, the night sky was a canvas filled with mysteries, a dome of glittering lights that sparked both awe and fear. Every ancient civilization developed its own story of what lay beyond, of how far space stretched, and of whether it had an end at all. These stories were not simply guesses, they were frameworks that explained human existence, morality, and destiny. The cosmos was never just a physical place. It was a spiritual landscape, a stage upon which gods acted, a place of order that mirrored or explained the lives of those who looked upward. In Mesopotamia, one of the world's earliest centers of civilization, the sky was seen as a kind of divine map. Babylonian astronomers kept meticulous records of celestial movements, connecting them with earthly events. For them, the heavens were not infinite. They were bounded by the gods. The sky was a series of layers, each ruled by different deities, and beyond those layers lay the domain of powers humans could not touch. The idea of the sky as a solid dome, sometimes imagined as a great inverted bowl, gave a clear answer to the infinite question. Space ended at the dome, and beyond it was the divine realm, inaccessible to mortals. This belief was not just religious, it shaped how people lived, how they saw their role in the universe, and how they predicted the future through astrology. In ancient Egypt, the heavens were woven into myth and ritual. The goddess Nut was often depicted as a vast arching figure, her body forming the sky itself, covered in stars. Beneath her lay the earth, represented by the god Jeb. Between them, the air god Shu kept them apart, maintaining the balance of existence. For Egyptians, the cosmos was orderly, cyclical, and eternal, but not infinite. Nut's arched body was both the ceiling and the boundary of the universe. Each night, the sun god Ra was swallowed by her mouth, traveling through her body to be reborn at dawn. The end of space was not a question to them, for the sky had a shape, a limit, a divine boundary that defined the known world. The ancient Greeks, however, pushed further toward abstraction. Philosophers such as Anaximander speculated about the apeiron, an infinite and boundless origin of all things. For him, the cosmos was not confined to a simple dome, but arose from something immeasurable. Yet most Greek cosmologies still described the universe as finite, often encased within celestial spheres. Plato imagined the cosmos as a perfect, finite structure, crafted by a divine craftsman, while Aristotle proposed a geocentric model in which Earth sat unmoving at the center, surrounded by nested, rotating spheres carrying the moon, sun, planets, and stars. Beyond the outermost sphere, Aristotle said, there was no space, no void, nothing at all. Space ended at the sphere of fixed stars, and to ask what lay beyond was meaningless in his framework. For centuries, this vision provided certainty. The universe was finite, ordered, and closed. In India, Vedic and later Hindu cosmologies took a different approach. Here, the universe was seen as cyclic, endlessly created and destroyed, with vast timescales beyond human comprehension. The concept of kalpas, or cosmic cycles lasting billions of years, suggested a universe without a simple beginning or end. Some texts describe the cosmos as infinite, with countless worlds existing in every direction, each sustained by different gods. Others describe it as layered, with multiple realms stacked above and below the human world. The infinite question here was not posed in the same way as in the West, because infinity itself was embraced as a spiritual truth. Space did not necessarily end, but it was filled with realms inaccessible to ordinary perception. Chinese cosmology offered yet another perspective. The traditional view, sometimes called the Gai Tian model, pictured the heavens as a dome covering a flat earth. This dome, vast and orderly, rotated overhead and regulated time and seasons. Later, more sophisticated models suggested a spherical earth under a spherical heaven, but still the universe was finite, bounded by heaven itself. The idea of infinity was not central. Rather, the emphasis was on harmony and balance between heaven, earth, and humanity. For ancient Chinese thinkers, what mattered was not whether space ended, but how the celestial order could be aligned with the moral and political order of society. Astronomy was deeply tied to governance, as emperors sought to legitimize their rule through alignment with the cosmos. In the Americas, indigenous peoples developed cosmologies deeply rooted in the natural environment. The Maya, for instance, viewed the universe as layered, with 13 heavens above and 9 underworlds below, connected by a cosmic tree or axis. The night sky was a sacred calendar, guiding agriculture, rituals, and kingship. For them, space was not infinite but structured, filled with gods and forces that influenced daily life. Similarly, the Navajo envisioned the sky as a blanket embroidered with stars, each placed there by deities in acts of creation. These cosmologies often described the universe as having edges, boundaries, or levels, but those boundaries were imbued with meaning rather than emptiness. Across all of these ancient traditions, one pattern is clear: the cosmos was never imagined as cold or indifferent. It was always meaningful, always inhabited, always connected to human life. To ask whether space ends, in ancient times, was not to ask about physical boundaries as modern science does, but about where the human world met the divine, where the known touched the unknown. The heavens were not empty expanses, but populated realms. The stars were not distant suns, but signs, spirits, or gods. The concept of infinite, endless space was rare, almost unsettling, because infinity suggested chaos, something beyond comprehension or order. For cultures built on cycles, hierarchies, and divine authority, it was far easier to imagine a bounded, structured cosmos than an infinite one. Still, in the cracks of these traditions, the idea of infinity appeared. In India's cyclic universes, in Anaximander's Aperon, in the suggestion that there might always be more beyond what is seen, humanity revealed a restless imagination. Even while most models painted the cosmos as finite and closed, there was always a sense that perhaps the mystery extended farther, that perhaps what was beyond could not be so neatly contained. That tension between a finite dome and an infinite expanse is the same tension we grapple with today. The ancient views of the cosmos remind us that the infinite question is not new. It is as old as the first time someone looked up and wondered what those stars were, how far away they lay, and whether the sky had a limit. Though their answers were shaped by myth, ritual, and limited observation, they represent the first great attempts to situate humanity within the universe. Each culture gave space an ending point, a boundary where human comprehension stopped and the divine began. And in doing so, they revealed that the question of whether space ends is not only about physics, but about meaning itself, about how we explain our place within something that seems immeasurable, unreachable, and endlessly mysterious. The early 20th century transformed humanity's understanding of the cosmos in ways that ancient thinkers could never have imagined. For centuries, the dominant framework of the universe had been rooted in Newtonian mechanics, a model in which space and time were absolute, and changing backdrops against which the drama of matter and energy unfolded. Newton's laws worked extraordinarily well to describe the motion of planets, the falling of apples, and the tides of the sea. Yet even as they became the foundation of modern science, they left deep mysteries unsolved. Chief among them was the nature of gravity, that invisible force, which seemed to reach across space and pull masses together. Newton himself admitted he did not know what gravity truly was. He could describe its effects with equations, but the underlying mechanism remained a puzzle. Into this puzzle stepped Albert Einstein, whose theory of general relativity did not simply revise Newton's view of the cosmos, it revolutionized it entirely. Einstein's breakthrough came from his realization that space and time were not fixed entities, separate and eternal. Instead, they were interwoven into a single fabric he called spacetime, a dynamic stage that could bend, stretch, and warp under the influence of matter and energy. Gravity, in this new vision, was not a mysterious force reaching across empty space. It was the curvature of spacetime itself. A massive body like Earth bends the spacetime around it, and objects moving nearby simply follow the natural curves of this geometry. To us, this looks like attraction, but in reality, it is motion along curved paths in a distorted spacetime landscape. This new framework had profound consequences for how we think about the universe. If space and time themselves are flexible, then the structure of the cosmos is not rigid or static. It can evolve, expand, contract, and change. Suddenly, the infinite question, does space end, had to be considered in an entirely new way. It was no longer enough to imagine space as a container with possible boundaries. Instead, space itself was revealed to be a participant in cosmic evolution, shaped and reshaped by the matter and energy within it. The question was no longer simply whether space stretched endlessly or stopped somewhere. It became a question of the geometry of spacetime itself. One of the most famous demonstrations of general relativity's power came in 1919, during a solar eclipse. Einstein predicted that light from distant stars passing near the sun would bend due to the curvature of spacetime around the sun's mass. When astronomers observed this deflection, they confirmed his theory, and Einstein became a global icon. The bending of light revealed that spacetime was not merely an abstract idea, but a physical reality that shaped the universe we inhabit. If spacetime could bend near stars, could it also curve on larger scales? Could the universe as a whole be curved, finite, or infinite depending on its geometry? These were the kinds of questions general relativity opened up. The mathematics of Einstein's theory allowed for many possible shapes of the universe. A universe with positive curvature could be like the surface of a sphere, finite, yet without edges, because one could travel indefinitely and eventually loop back to the starting point. A universe with zero curvature could be flat and infinite, extending without end in every direction. A universe with negative curvature could be like a saddle, infinite, but shaped in a way that diverges forever. Each possibility carried profound implications for the infinite question, because in Einstein's universe, the end of space was no longer a simple boundary, but a question of geometry and curvature. In 1917, Einstein himself attempted to apply his equations to the entire cosmos. He envisioned a static, eternal universe, neither expanding nor contracting, because that fit the philosophical assumptions of the time. To make this work, he introduced a term into his equations called the cosmological constant, a kind of repulsive force that counteracted gravity and held the universe steady. But this static solution turned out to be unstable, and later discoveries would reveal that the universe was not static at all. Still, Einstein's attempt to describe the whole cosmos within the framework of general relativity marked a turning point. It suggested that the universe itself could be described scientifically, not just mythologically, and that its structure was written into the fabric of spacetime. What followed was a profound reimagining of cosmic boundaries. If space could curve back on itself, then perhaps the universe was finite but unbounded, like the surface of Earth. A traveler walking in one direction on Earth would never find an edge but would eventually circle back. In the same way, a finite but curved universe would have no walls, no stopping points, but still not be infinite in volume. Alternatively, if the universe were flat or negatively curved, it could extend without end, making infinity the natural answer. Einstein's equations did not dictate which was true. They allowed multiple possibilities, and it would take observations to determine which path reality had chosen. The theory of general relativity also introduced the concept of black holes, regions where spacetime is curved so intensely that not even light can escape. At first, Einstein himself was skeptical of their existence, but later evidence showed they were real. Black holes posed yet another challenge to the infinite question, for within their depths spacetime itself seemed to come to an end in a singularity, a point of infinite density. Did this mean space could end in some places while continuing elsewhere? Or did it mean our equations broke down at those extremes? Either way, black holes revealed that the structure of space was not smooth and simple, but full of strange possibilities. General relativity also changed how we think about time. In Newton's framework, time was absolute, flowing uniformly everywhere. In Einstein's universe, time was intertwined with space, bending with it. Near a massive object, time slows down relative to regions farther away. This effect, known as time dilation, has been confirmed by experiments and even affects the operation of GPS satellites today. If space and time themselves are malleable, then the idea of boundaries becomes even more complex. Where does space end if time itself is part of the same fabric? Can we imagine an end of space without also confronting the possibility of an end of time? These are the kinds of questions general relativity forces us to consider. The elegance of Einstein's theory lies in its ability to describe the universe on both cosmic and intimate scales. It governs the bending of light around galaxies, the motion of planets, and the ticking of clocks. Yet at its heart, it also provides a framework for addressing the infinite question in ways that ancient thinkers could not. No longer is space imagined as a dome or a ceiling, no longer as a fixed container holding stars like lanterns. Instead, space is alive, dynamic, and deeply connected to the matter and energy within it. If the universe is finite, it is not bounded by walls but by its own geometry. If it is infinite, then its infinitude arises naturally from the flatness or openness of spacetime. Einstein's universe was not the final word, of course. It laid the foundation for later discoveries, such as the expanding universe revealed by Edwin Hubble, the cosmic microwave background radiation that traced back to the Big Bang, and the accelerating expansion attributed to dark energy. But it was Einstein's framework that made these discoveries possible. Without the revolution of general relativity, we might still imagine the cosmos as static and unchanging, never suspecting that it could be finite, infinite, curved, or expanding. Einstein gave us the tools to think about space, not just as something that might end or not end, but as something whose very structure could be measured, tested, and explored. When Albert Einstein's equations of general relativity were first applied to the cosmos, the expectation was that the universe would be static, eternal, and unchanging on the largest scales. Yet the mathematics of those very equations hinted otherwise. Unless a balancing force was added, the mutual pull of gravity should either cause the universe to collapse inward or push it outward in expansion. For a time, Einstein resisted this implication, introducing his famous cosmological constant to hold the universe steady. But nature had other plans. In 1929, Edwin Hubble, observing through the massive telescope on Mount Wilson in California, made a discovery that forever changed our view of the cosmos. Distant galaxies were not static at all. They were rushing away from us. Their light stretched into longer, redder wavelengths, a phenomenon now called redshift. This observation was the first undeniable evidence that the universe is expanding. The expanding universe reshaped the infinite question in dramatic ways. For centuries, the debate had centered around whether space stretched endlessly or whether it ended at some cosmic boundary. But Hubble's discovery introduced a new twist. The universe was not fixed, but dynamic, growing larger with every passing moment. This meant that the very fabric of space itself was stretching, carrying galaxies with it. The expansion was not like an explosion of matter into empty surroundings. Instead, space itself was swelling, like the surface of a balloon being inflated. Dots on the balloon, representing galaxies, move apart not because they are traveling across the balloon, but because the balloon's surface is expanding beneath them. Likewise, galaxies are not flying through pre-existing space, but being carried apart as the universe itself grows. This revelation opened the door to the concept of the Big Bang, a moment roughly 13.8 billion years ago when the universe was in an unimaginably hot, dense state and began expanding. From that moment, space and time themselves have been unfolding together, stretching into the vast cosmos we see today. The Big Bang did not occur in a place within space. It was the origin of space itself. This challenges our intuition. When we ask, what is the universe expanding into? The answer is subtle. It is not expanding into anything. Space itself is growing, and the question of what lies outside the universe has no clear meaning, because space is the totality of what exists. For the infinite question, does space and the expanding universe complicates matters? If space is growing larger over time, does this mean it will grow forever, becoming infinite? Or will it eventually stop expanding, perhaps collapsing back into a singular end? Early cosmologists debated these scenarios intensely. Some argued that gravity, pulling on all matter, might slow the expansion and eventually reverse it in a big crunch. Others imagined that the expansion might continue but gradually slow, approaching a halt as the universe stretched thinner. Still others entertained the possibility of eternal expansion, with galaxies moving farther and farther apart until the cosmos became a cold, dark, and lonely place. Each possibility suggested a different fate for the question of space's end. Observations of galaxies became crucial in resolving this debate. By measuring how fast galaxies were receding at different distances, astronomers could infer the rate of expansion and how it was changing over time. This is encapsulated in what we call Hubble's law. The farther away a galaxy is, the faster it recedes. This law is not just an observation. It is a consequence of uniform expansion. Every observer, no matter where they are in the universe, would see galaxies receding in this way, because expansion is not about motion through space, but the stretching of space itself. The expanding universe also introduced the concept of the observable horizon. Because light travels at a finite speed and the universe has a finite age, there is only so far we can see. Beyond a certain distance, the light from galaxies has not had enough time to reach us. This observable universe forms a sphere around us, about 93 billion light-years in diameter, but it is not necessarily the entire universe. The expansion means that galaxies beyond that horizon may exist, but we can never observe them, because space between us stretches faster than light can bridge. For the infinite question, this creates a profound distinction. The universe we can see is finite, but the total universe may be infinite, hidden beyond the horizon. As scientists studied expansion more deeply, they discovered it was not uniform. Through time, for the first few billion years after the Big Bang, gravity slowed the expansion as galaxies pulled on one another. But about 5 billion years ago, something unexpected happened. Instead of slowing further, the expansion began to accelerate. Galaxies started moving apart faster and faster, as if some mysterious force was pushing the universe outward. This force has been called dark energy, and though its nature remains unknown, its effects are clear. Dark energy now dominates the universe, driving expansion at an ever-increasing pace. If this continues indefinitely, the universe may face a future of eternal acceleration, where galaxies speed away from one another so rapidly that eventually, only our local group of galaxies will remain visible. The discovery of accelerating expansion deepens the infinite question. If space continues to grow forever, faster and faster, then the universe may truly be infinite in the future, even if it was not infinite at the beginning. Galaxies will drift beyond reach, stars will burn out, and the universe will become a vast, cold void. Some theories suggest even more extreme scenarios, such as the Big Rip, in which acceleration becomes so strong that galaxies, stars, planets, and even atoms themselves are torn apart by the expansion of space. In this vision, space does not end with a boundary, but with the catastrophic unraveling of everything within it. The expanding universe also raises questions about what infinite really means. If the universe is spatially infinite today, was it always infinite, even at the Big Bang? How can something infinite expand? The answer lies in the mathematics of relativity. It is possible for an infinite universe to expand, becoming larger in the sense that the distances between galaxies increase, even though it has no overall edge. Alternatively, the universe may be finite but unbounded, like the surface of a sphere. In that case, expansion makes the sphere larger, but it still has no edge. Both scenarios are consistent with the physics we observe, and deciding between them remains one of cosmology's great challenges. The imagery of expansion also invites philosophical reflection. If the universe is expanding, does that mean there was once a time when there was nothing? The Big Bang theory suggests not, because the Big Bang was not an explosion into emptiness, but the creation of spacetime itself. Asking what came before the Big Bang may be as meaningless as asking what lies north of the North Pole. Yet the human mind struggles with this. We are accustomed to beginnings and endings, to things starting in places and moving into spaces that already exist. The expanding universe asks us to stretch beyond these intuitions, to imagine creation not within space, but as space. As the universe continues to expand, its very structure changes. Galaxies cluster together under gravity, forming vast filaments and voids in a cosmic web that stretches across billions of light years. On smaller scales, stars form, live, and die, enriching the cosmos with heavier elements that create planets and life. All of this unfolds within a framework of expansion, an ongoing stretching of the fabric of reality itself. The question of whether space ends becomes entangled with the question of what kind of universe expansion has created. If the cosmos is infinite now, then space does not end. If it is finite but unbounded, then space ends nowhere, even though it is limited in volume. If expansion continues forever, the distinction between finite and infinite may eventually lose meaning, as the observable universe shrinks and the rest slips beyond reach. What makes the expanding universe so profound is that it ties the infinite question not only to the structure of space, but also to the fate of time. If the universe expands forever, then time itself may stretch endlessly, carrying existence into an eternal future. If the universe were to collapse in a big crunch, time itself might have an end. In either case, the expanding universe ensures that the question of whether space ends is not a static one. It is dynamic, changing with every passing second, written into the ongoing story of cosmic evolution. When we look up into the night sky, what we see is far from the full story. The stars that twinkle above us, the faint glow of the Milky Way stretching across the darkness, and even the distant galaxies captured by powerful telescopes represent only a small fraction of what is truly out there. This distinction lies at the heart of one of the most fascinating concepts in modern cosmology, the difference between the observable universe and the entire universe. Understanding this difference is essential to approaching the infinite question, because it highlights the limits of our perception and reminds us that the cosmos is larger, stranger, and more mysterious than our senses or even our instruments can reveal. The observable universe is, quite literally, the part of the universe we can observe. It is defined not by physical walls or cosmic barriers, but by the speed of light and the age of the universe. Light, though incredibly fast, is not instantaneous. It takes time for light to travel across space. When you look at the moon, you are seeing it as it was about 1.3 seconds ago. When you look at the sun, you are seeing it as it was 8 minutes ago. When you look at distant galaxies, you are seeing them as they were millions or even billions of years ago. The farther we look, the further back in time we see, because light takes longer to reach us. Now, because the universe is about 13.8 billion years old, you might expect that the maximum distance we can see would be 13.8 billion light years. But the situation is more complex. During those billions of years, space itself has been expanding, stretching the paths that light must travel. This means that the most distant light we can observe today comes from regions now much farther away than 13.8 billion light years. Taking into account this expansion, the radius of the observable universe is about 46 billion light years, giving it a diameter of roughly 93 billion light years. This observable sphere surrounds us, with Earth at the center, not because we are in a special place, but because every observer anywhere in the universe would see their own observable sphere centered on themselves. Within this vast sphere are hundreds of billions of galaxies, each containing hundreds of billions of stars, along with countless planets, clouds of gas and dust, and mysterious dark matter. This is the universe as we know it through observation, the portion accessible to our telescopes and instruments. Yet beyond that sphere lies the unknown. The entire universe may extend far past what we can see, possibly infinitely. The observable universe is like standing on the shore of a vast ocean. You can see the waves stretching out to the horizon, but you know the ocean continues beyond it. The horizon does not mark the end of the ocean. It only marks the limit of your sight. This cosmic horizon is called the particle horizon, the maximum distance from which light has had time to reach us since the beginning of the universe. Beyond this horizon, there may be galaxies, stars, and entire structures we will never observe, no matter how long we wait or how powerful our telescopes become. That is because the expansion of space ensures that some regions recede from us faster than light itself, carrying them forever beyond our view. These galaxies exist in reality, but not in our observable universe. The difference between observable and entire universe forces us to think carefully about the concept of edges. To ancient peoples, the edge of the cosmos was the dome of the sky, the limit of visibility. To us, the edge is the particle horizon, the limit of observability, but neither represents an actual boundary of existence. Just as the ancient dome was an illusion created by perception, our observable limit is not the end of space. It is a horizon, shaped by the finite age of the universe and the finite speed of light. The entire universe may continue indefinitely, in all directions, unending and unbounded, beyond what we can ever access. This distinction also raises a profound question. If we can never see beyond the observable universe, can we ever know what lies there? Scientific theories attempt to extrapolate For example, measurements of the cosmic microwave background radiation, the faint afterglow of the Big Bang, suggest that on large scales, the universe is remarkably uniform. Galaxies are distributed in similar ways in every direction we look, and the cosmic background is nearly the same in temperature across the sky. This uniformity implies that what lies beyond our horizon may be similar to what we see within it, though we cannot prove this. Some cosmologists argue that the entire universe is likely much larger than the observable universe, perhaps infinite. Others suggest it might be finite but unbounded, like the surface of a sphere that curves back on itself. The concept of the observable universe also reshapes our understanding of time, because looking farther into space is also looking further into the past. The edge of the observable universe is the ultimate time machine. When we peer at the most distant galaxies, we are not seeing them as they are today, but as they were billions of years ago. At the very edge of observability, we can glimpse the universe as it was just 380,000 years after the Big Bang, when atoms first formed and light could travel freely. This is the cosmic microwave background, a faint radiation that fills the sky. It is not the end of space, but it is the farthest wall of light we can see, the most ancient signal the universe has left for us to detect. The contrast between observable and entire universe also touches on the nature of scientific humility. We often speak as though we understand the cosmos, but in truth, we only know a fraction of it. Our observable sphere, vast though it is, may be an infinitesimal sliver of the whole. If the universe is infinite, then the observable universe is like a tiny window into an endless expanse. If the universe is finite but larger than the observable portion, then we are like explorers mapping only one continent while entire worlds remain hidden. The boundary between observable and entire reminds us that science, though powerful, has limits defined by nature itself. This limitation does not discourage discovery. Rather, it makes discovery more poignant. Knowing that the observable universe is finite forces us to ask sharper questions about what we see. Why does the universe appear so uniform across regions that could never have communicated with one another? This puzzle, known as the horizon problem, led to the theory of cosmic inflation, a brief period of rapid expansion in the early universe that stretched space so fast that regions once in contact were flung far apart. Inflation suggests that the universe may be far larger than what we can observe, perhaps unimaginably so. In this way, the observable universe is not just a limit, but also a clue, hinting at processes beyond our sight. There is also a human dimension to this distinction. When people gaze at the stars, they often feel small, humbled by the immensity of what they see. Yet what we see is only a fragment, a tiny piece of a reality much larger than our imaginations can easily contain. The knowledge that there is more beyond, that the entire universe dwarfs the observable one, can deepen that sense of awe. It can also provoke reflection on our place within it. If the observable universe alone contains hundreds of billions of galaxies, how many more lie beyond? If the observable universe spans 93 billion light-years, how much larger or infinite might the entire cosmos be? The observable and entire universe distinction also highlights the interplay between knowledge and mystery. The observable universe is the realm of data, evidence, and measurement. It is what we can study, chart, and test. The entire universe is the realm of speculation, theory, and imagination. It is where science meets philosophy, where mathematics extends beyond observation, and where the infinite question becomes most acute. The two are inseparable. Without the observable, we would have no anchor for our theories. Without the entire, we would have no horizon for our wonder. The more we learn about the observable universe, the sharper the infinite question becomes. If the observable universe has no physical edge, then perhaps the entire universe also has no edge. If the observable universe is only a portion, then the true cosmos may be infinite, unending, forever beyond the reach of our instruments. And yet, even in its incompleteness, the observable universe tells us something profound, that existence is vast, structured, and ancient, and that we are participants in a story written across billions of light-years. By distinguishing between what we can see and what exists beyond sight, we come closer to understanding the scope of the question itself. When we speak of the universe, we often imagine it as a vast, open expanse stretching endlessly in all directions. Our minds instinctively picture space as something like a flat plane or a great void without limit. Yet cosmology has shown us that this is not the only possibility. The universe might not be flat and infinite at all. Instead, it could have a particular shape, a geometry dictated by the laws of physics and the total amount of matter and energy it contains. The question of shape is not trivial, nor is it purely abstract. The geometry of the cosmos determines whether space extends forever or loops back on itself, whether it has boundaries or none, whether it is infinite or finite. Understanding the potential shapes of the universe is, therefore, central to asking whether space ends. Einstein's general theory of relativity opened the door to this line of inquiry by revealing that space is not a passive stage on which events unfold, but an active participant, capable of bending, stretching, and curving in response to the presence of matter and energy. Just as a heavy ball placed on a rubber sheet causes the sheet to curve, so do stars, galaxies, and dark matter cause the fabric of space-time to curve. On small scales, we see this curvature in the bending of starlight around the sun, or in the warping of space near black holes. But on the largest scales, the collective influence of all the matter and energy in the universe determines the geometry of the cosmos itself. Cosmologists generally classify the possible shapes of the universe into three categories: closed, open, and flat. These are not just arbitrary labels but precise descriptions rooted in mathematics. A closed universe has positive curvature, like the surface of a sphere. An open universe has negative curvature, like the surface of a saddle. A flat universe has zero curvature, like an infinite sheet of paper. These different geometries each imply different answers to the question of boundaries and endings. In a closed universe, space would be finite but unbounded. This may sound paradoxical, but an analogy helps. Imagine standing on the surface of Earth. The surface is finite. You could travel around it and eventually return to your starting point, but it has no edge. You never encounter a cliff where the planet ends. Similarly, if the universe were closed, you could, in theory, travel in one direction forever and eventually return to where you started, without ever encountering an edge. This model appeals to human imagination because it resolves the unsettling idea of an edge to existence, while still allowing for finitude. A closed universe is like a cosmic sphere, self-contained and looping back on itself. An open universe, by contrast, would be infinite and unbounded. Picture a saddle shape extending endlessly in every direction. In this geometry, the universe has no closure, no looping path that brings you back. Instead, it stretches outward forever, its negative curvature ensuring that parallel lines eventually diverge. In such a cosmos, space has no end and no boundary, extending endlessly into the unknown. This model satisfies the intuition of those who feel that infinity is the most natural state of the cosmos, though it confronts us with the incomprehensible vastness of an unending universe. A flat universe, the third possibility, also implies infinity in extent. Like a sheet without curvature, it stretches without end in all directions. However, it differs from the open model in its geometry. In a flat universe, parallel lines remain parallel. The familiar rules of Euclidean geometry apply. This infinite flatness is difficult to grasp because our daily experience is filled with curvature spheres, arcs, circles, but on cosmic scales, measurements suggest that space behaves almost perfectly flat. To determine which of these models describes reality, cosmologists rely on observations. One of the most powerful tools for this is the cosmic microwave background radiation, the afterglow of the Big Bang. By studying slight fluctuations in this ancient light, scientists can measure the curvature of the universe with extraordinary precision. Current data suggests that the universe is very close to flat, with only a tiny margin of error. If true, This would mean space extends infinitely, with no end. However, because our observations are limited to the observable universe, we cannot rule out the possibility that on larger scales, space curves back on itself. The margin of error leaves room for speculation. Beyond the closed, open, and flat categories, other exotic shapes are also possible. Some cosmologists have proposed that the universe could have a topology more complex than simple curvature. For example, it could be shaped like a three-dimensional torus, a donut shape. In such a universe, traveling far enough in one direction could eventually bring you back to your starting point, but with the geometry different from that of a sphere. A toroidal universe would be finite, but without boundaries, looping in ways that are difficult to visualize in 3 dimensions. Other models suggest even stranger topologies, where space could connect to itself in unexpected ways, creating a kind of cosmic hall of mirrors in which distant galaxies we observe might actually be multiple images of the same object seen from different paths of light. These theories of shape are not just abstract curiosities. They connect directly to the fate of the cosmos. A closed universe might eventually stop expanding and collapse back in a big crunch. An open or flat universe might expand forever, growing colder and emptier with time, ending in a heat death. Thus, the question of geometry is also the question of destiny. The possibility of a finite yet unbounded universe is especially compelling because it offers a resolution to one of humanity's most persistent questions: what lies beyond? If the universe loops back on itself, then there is no beyond. The cosmos is self-contained, with no need for an edge. This challenges our linear way of thinking, in which everything must have a start and an end, a boundary and a beyond. Instead, it suggests a reality more like a circle than a line, more like a globe than a map. At the same time, the possibility of an infinite universe confronts us with the truly unimaginable. Infinity is not just large, it is without limit. In an infinite cosmos, there could be infinite galaxies, infinite stars, and even infinite versions of ourselves, playing out infinite variations of existence. This raises questions not just of science, but of philosophy. Can infinity exist in reality, or is it only a concept of mathematics? If the universe is infinite, then our observable sphere is like a single grain of sand on an endless beach. If it is finite but boundless, then we are part of a vast but self-contained whole, looping in ways our minds can scarcely imagine. Ultimately, the question of the universe's shape remains unsettled, though evidence points strongly toward flatness. Yet even this does not end the debate, because flatness may hold only within our observable sphere. Beyond it, space could curve, twist, or fold in ways we cannot detect. Theories of shape remind us that space is not an empty nothingness, but a structure, a fabric with properties that can be measured, tested, and imagined. It is a fabric woven not just of matter and energy, but of possibility, stretching our minds as surely as it stretches our instruments. The idea of cosmic boundaries or their absence carries with it both comfort and unease. A closed universe spares us the vertigo of infinity, but it places us inside a cosmic sphere whose surface we can never see in its entirety. An infinite universe offers no boundaries, but challenges our ability to comprehend endlessness. A toroidal universe or other exotic topology defies our imagination altogether, hinting that reality may be stranger than any analogy we can craft. Each possibility forces us to rethink what it means for something to end or to exist. As vast as our universe appears, as endless as the galaxies seem when scattered across the night sky, modern cosmology suggests that the cosmos we know may be only one piece of a much larger puzzle. The idea of a multiverse, the possibility that our universe is not unique, but one among many, emerges naturally from the very theories that explain the origin and structure of space itself. To ask whether space ends is to eventually encounter this possibility, because if our universe has limits, if it is finite or curved or bound in some way, then what lies beyond those limits might not be nothingness, but other universes, perhaps, with different properties, different laws of physics, or even no connection to ours at all. The multiverse transforms the question of boundaries from, does space end? Into, does our space connect to others we cannot see? The concept of a multiverse is not new, though it has taken on more rigorous scientific meaning in recent decades. Ancient philosophers speculated about countless worlds, infinite and varied, populating an endless cosmos. In some traditions, these worlds were thought of as parallel realms, each with its own order and inhabitants. Today, while the language has changed, the essence of the idea persists. Scientists, guided by mathematics and observation, suggest that our universe may be just one region of a much larger reality, a bubble floating in an ocean of other bubbles, or a single vibration in a vast symphony of possibilities. One of the leading scientific frameworks that hints at a multiverse is the theory of cosmic inflation. According to inflation, in the first fraction of a second after the Big Bang, the universe underwent a period of rapid, exponential expansion, ballooning faster than the speed of light. This inflationary process smoothed out the cosmos, creating the nearly uniform universe we observe today. Yet some versions of inflationary theory predict that this process never completely ended. Instead, it continues in other regions of space, endlessly creating new, pocket universes, while inflation stops in certain areas to form universes like ours. This idea, known as eternal inflation, paints a picture of a cosmos in which universes are constantly budding off from an inflating background, each one potentially with its own properties, dimensions, and constants of nature. If eternal inflation is correct, then our universe may be one bubble in a vast froth of bubbles, each forming, expanding, and existing independently. Some of these universes might be similar to ours, governed by familiar physics, filled with galaxies and stars. Others could be wildly different, with physical laws so alien that matter as we know it could not exist. The multiverse becomes not just a possibility, but an inevitability of the inflationary framework, a natural outcome of the very physics that explain why the cosmos appears as it does today. Another scientific path that points toward the multiverse comes from string theory, a leading candidate for uniting the forces of nature under a single framework. String theory proposes that the fundamental building blocks of reality are not particles, but tiny vibrating strings, existing in higher dimensions beyond the familiar three of space and one of time. The mathematics of string theory allows for a vast landscape of possible solutions, each corresponding to a different way the extra dimensions could be compactified. These different configurations lead to different laws of physics, different constants, and different properties of space-time. Some theorists suggest that each configuration corresponds to a different universe within a multiverse. In this view, the multiverse is not merely speculative, but a natural consequence of the richness of the mathematics. Our universe, with its particular physical constants that allow stars and life to exist, is just one valley in a vast landscape of possible realities. Quantum mechanics also hints at multiverse-like possibilities. In the many worlds interpretation of quantum theory, every quantum event branches into multiple outcomes, each realized in a separate universe. According to this interpretation, whenever a particle has multiple possible states, the universe splits, with each possible outcome occurring in a different branch. This creates an ever-branching tree of universes, unimaginably numerous, encompassing every possibility of every event. In this quantum multiverse, there are universes where history unfolded differently, where choices led to other futures, where entire cosmic histories diverged from our own. The philosophical implications of the multiverse are as staggering as the scientific ones. If the multiverse exists, then our universe is not the entirety of reality, but a small part of a greater whole. This raises questions about uniqueness, meaning, and significance. For centuries, humanity has struggled with the realization that Earth is not the center of the cosmos, that our sun is one of many stars, that our galaxy is one of countless others. The multiverse extends this humbling trajectory even further. Our universe itself may be one of countless universes, no more central or special than Earth was to the ancient sky, the multiverse also offers potential explanations for some of the greatest mysteries of physics. One such mystery is the fine-tuning of the universe. The physical constants of nature, the strength of gravity, the charge of the electron, the rate of expansion appear to be finely tuned to allow for the existence of stars, planets, and life. Change these values even slightly, and the universe as we know it would collapse into a lifeless void. Why should the laws of physics be so precisely set for life? In a single universe, this seems improbable, but in a multiverse with countless universes, each with different laws, it is inevitable that some universes will have the right conditions for life. We happen to inhabit one of them, not because the universe was designed for us, but because in universes without life, no observers would exist to ask the question. This anthropic reasoning, while controversial, gains power in the context of the multiverse, yet the multiverse raises challenges as well. If other universes exist beyond our own, can we ever observe them? By definition, other universes are beyond our cosmic horizon, disconnected from our observable sphere. Some may be forever out of reach, no matter how powerful our instruments. Critics argue that this makes the multiverse unscientific, a matter of speculation rather than empirical science. Others counter that indirect evidence may still be possible. For example, collisions between bubble universes in the inflationary multiverse might leave faint imprints in the cosmic microwave background radiation, or the statistical distribution of physical constants across universes might explain why ours has the values it does. In this way, the multiverse, while difficult to test directly, may still provide scientific insights. The multiverse concept also challenges our sense of boundaries. If space is infinite and filled with countless bubble universes, then the question of whether space ends becomes less relevant. Our universe may have boundaries of observability, but beyond them lies not emptiness, but other universes, stretching outward endlessly in a higher dimensional reality. If the quantum multiverse is real, then every moment in our lives is accompanied by countless alternate versions in parallel worlds. If the string theory multiverse exists, then every possible configuration of physical law is realized somewhere. In some universe, in each scenario, the end of space is replaced by the continuation of existence in other forms. Culturally and imaginatively, the multiverse resonates deeply. It fuels science fiction, philosophy, and even spiritual reflection. The idea that there are other universes, perhaps with other versions of ourselves, stirs both wonder and unease. It suggests that reality is far stranger and richer than we ever dreamed, and that the universe we inhabit, vast though it seems, is just one page in an infinite book. The multiverse stretches the human imagination to its limits, forcing us to confront the possibility that our universe is not the whole story, that the cosmos does not end at the edges of what we can see, or even at the edges of what we can conceive. When we stand beneath the night sky, gazing into the scattered diamonds of starlight, the question of whether space ends is not merely scientific, it is also deeply human, a question that touches the heart as much as the mind. Science can describe the curvature of space, the expansion of the cosmos, and the possibility of other universes, but the meaning of all this vastness is something each person must wrestle with in quieter moments. To consider whether space ends is to consider our place within it, to ask what it means to live in a universe that may be infinite or finite, bounded or boundless, and to reflect on how that knowledge shapes our sense of existence. From the earliest days of human thought, the heavens have stirred philosophical wonder. Ancient peoples looked upward not only to chart the seasons or navigate their journeys, but to seek meaning in the patterns of the stars. The sky was a canvas onto which they projected myths, deities, and stories of origin. The question of whether the cosmos had an edge was intertwined with questions of why we exist and what role humanity plays in the great order of things. In many traditions, the boundary of the sky was seen as a sacred veil, marking the division between the human world and the divine. Today, though science has replaced myth with equations and telescopes, the feeling that the universe is a mirror for our search for meaning has not diminished. the thought that space might be infinite stirs both awe and unease. Infinity is not simply large. It is beyond measure, beyond human comprehension. If space truly stretches endlessly, then every direction, every horizon, holds more galaxies, more stars, more worlds without end. For some, this idea is comforting, suggesting a cosmos without limits, rich with possibilities. For others, it is overwhelming, a reminder of how small and fleeting human life is against the backdrop of eternity. The infinite cosmos dwarfs us, yet it also invites us to imagine ourselves as part of something so vast that it cannot be contained. To live in an infinite universe is to accept that our personal lives are threads woven into a fabric that has no edge. A finite universe, on the other hand, offers a different kind of meaning. If the universe is closed, looping back on itself like the surface of a sphere, then space is vast but self-contained, whole within itself. There is no beyond, no endless stretch of unknown territory, only a cosmos that is complete. This vision, too, has philosophical resonance. A finite yet boundless universe can be seen as harmonious, balanced, and self-sufficient, a structure that contains everything necessary within itself. For those who find the idea of infinity unsettling, the notion of a closed cosmos brings a sense of closure, an assurance that existence has form, even if it has no walls. The multiverse adds yet another dimension to the philosophical picture. If our universe is one among many, then the meaning of existence becomes even more complex. Are we unique, or are there countless versions of ourselves in other realities? Is our universe special, or just one variation among infinite possibilities? The multiverse raises questions not only about physics, but about identity, purpose, and chance. If there are infinite universes, then every possibility is realized somewhere. Does that diminish the significance of our choices, or does it make this version of reality, the one we experience, even more precious? Some philosophers suggest that the multiverse, far from stripping away meaning, deepens it, reminding us that we are participants in a reality so vast and varied that no single narrative could encompass it. The human mind struggles to reconcile these possibilities, yet, in the struggle itself lies meaning. To ask whether space ends is to confront the limits of our understanding, to accept that there may be questions with no final answer. This acceptance is not defeat, but humility, a recognition that we are finite beings contemplating the infinite. In this humility, there is a kind of beauty. It reminds us that knowledge is not only about answers, but about wonder. That science is not only about measurement, but about awe. The pursuit of cosmic truth becomes less about conquering the unknown, and more about living fully within it. Philosophers have long reflected on the relationship between humanity and the cosmos. For some, the vastness of space underscores our insignificance, suggesting that human life is a fleeting accident in an indifferent universe. For others, the very fact that we can contemplate the universe is evidence of our significance. The stars may not notice us, but we notice them, and in that noticing we create meaning. The cosmos may be vast, but the human capacity to wonder, to ask, and to dream stretches across it like a bridge. In this sense, the question of whether space ends is less about the universe and more about ourselves. It asks us to consider how we define value, purpose, and belonging in a reality that is far larger than our daily lives. On a more personal level, reflecting on whether space ends can change the way we see our own lives. Knowing that the universe may be infinite can make our struggles feel small, yet it can also put them into perspective, reminding us that life is precious because it is brief. Knowing that the universe may be finite can encourage us to see ourselves as part of a whole, connected to the cosmos in ways we do not fully grasp. Either way, the contemplation of cosmic boundaries enriches our understanding of what it means to be human. It teaches us to hold both awe and humility, both curiosity and acceptance, both the desire to know and the willingness to live with mystery. The question also connects us to the long human tradition of wonder. When we ask whether space ends, we are joining a conversation that spans cultures and centuries. We are standing alongside ancient astronomers who charted the stars, philosophers who pondered infinity, poets who sang of the heavens, and scientists who mapped galaxies. To ask this question is to participate in the shared human journey of seeking meaning in the face of the unknown. It is a reminder that we are not alone in our wonder, but part of a lineage of seekers stretching back to the dawn of consciousness. In the end, whether space ends or continues forever, whether it is one universe or many, whether it loops back on itself or stretches into infinity, the meaning we find lies not only in the structure of the cosmos, but in our response to it. The universe invites us to imagine beyond ourselves, to place our small lives within a context so vast that it changes how we see everything. To wonder about the boundaries of space is to expand the boundaries of our own minds, to step outside the narrow frame of daily concerns and glimpse the horizon of eternity. And in that glimpse, we find something essential not just about the universe, but about ourselves as we have drifted together through this journey, moving gently from the infinite question to ancient views, from Einstein's curved space to Hubble's expanding cosmos, from the boundary of the observable universe to the strange possibilities of its shape, from the tantalizing whispers of a multiverse to the philosophical depths of human meaning. We find ourselves not at an answer, but at a place of stillness. The question of whether space ends remains one of the greatest mysteries, a question science continues to pursue with mathematics, telescopes, and imagination. Yet what matters, as you rest beneath this sky of thought, is not whether the universe is finite or infinite, but that the act of wondering connects you to it. Every galaxy, every star, every beam of ancient light that has traveled billions of years to touch your eyes, becomes a reminder that you are part of this story. Space may end, or it may not. It may loop back on itself, or stretch without limit, or exist as one of countless realities. But tonight, as you lie in stillness, what matters is that you belong within it. That your life is a thread in its fabric, brief, yet luminous, finite, yet full of meaning. The universe does not need to end for you to feel its embrace. It does not need to reveal its edges for you to know its wonder. To wonder at all is to already hold infinity within yourself.